All right. Good. So let's start some convergence, new convergence. Because for the last 10 days, at least last week, you have seen so many methods. So probably one more method, but I'm not going to apply my method to the homogenization because I allotted 3 lectures. Out of that, I will be giving 2 lectures on gamma convergence in a general setup. And then as an application of gamma convergence, Harsha will give 1 lecture, its application to homogenization. So that's the plan. So I will not be talking any homogenization in this homogenization discussion meeting. Okay. It is hidden. Okay. So this is because it's a method rather developed probably independently. Probably this is the first method in the 1970s, even in the nascent stage of homogenization. Homogenization was there from material science for ages, but the mathematical theory of homogenization started to come up in the beginning of 1970s. And this was also more or less came at that time, and this was introduced mainly to study what we call it a minimization problems, or because of that name, it's also called the variational convergence. So I'm going to introduce that slowly, the concept of variational convergence, what is this minimization problem, and I will try to connect with your problems in the thing. So I'm not going to prove because just 2 lectures, it's a huge topic by itself. Even without homogenization, you may take a course or something to understand the fully things about in the more general topological spaces and all that. So, but there is it's a little old book, maybe 1990s or something, a book by, so you have gamma convergence. Okay. In notation, we have this gamma convergence. This book is by G. Dalmaso, and there are many articles like due to Butaso and other people. This is an introduction to gamma convergence itself. It's a nice book to read. So it gives you the full book is on gamma convergence. Okay. So you can go through that. It is given in a general abstract topological spaces. The definitions in abstract topological spaces may little time for you to understand, but what I'm going to do it, I will do it in a general metric space. And topological spaces, you have to work with neighborhood systems and all that, but it's the same thing. So for our underlying space is a metric space all the time. I will not mention any more this one. But for our applications, you will see X can be an H1 of omega, W1P of omega, H1 naught of omega. It can be various spaces like that. So what's the minimization problem, typically? So you have a function f from x to r, and most of the time we will take r bar. This is the extended real line. You will see why we do that. Because many problems can be put it in R bar by defining values plus infinity in the place where you want to extend to a bigger space. And that way the minimization problem will not get affected, but the space you are studying will change. So you can study in a different way. So it's the extended real number. So what's basically a minimization problem? You are looking for infimum of f of y with y in x. So if their x is x, so the problem is look for an x in x such that f of x is equal to infimum of, yeah, okay. So x in x, you look for that. If such an x exists, this infimum becomes a minimum. Okay, so that is the thing. So the infimum can be replaced by a minimum when there is a solution. So when you say that my minimization problem f has a solution, it means that there is an x satisfying that. So that's a point you want to understand. Okay, so the problem is clear. So this is what we will be talking in an abstract setting. Little bit. Then we'll go to that one. We'll see examples. We are going to have these lectures through examples. And my idea of these 2 lectures is to introduce various notions associated with it, understand some of the concepts, and I can define the gamma convergence in one line right from the beginning without going to any of that one, but you will see the definition at the end of my class, almost in the second half of my second lecture. So we are setting a stage and setting the motivation, why we want to study, why it is a kind of natural definition, so that you get it automatically, the definition of that one. Okay? So what are the first thing you would say that, so if I call this infimum equal to alpha, alpha is equal to, this can exist all the time. Because we are in the extended real line, it can possibly be minus infinity, doesn't matter. When f is identically infinity, the minimum is infinity. Okay, so you naturally assume x is a non-empty set. So you don't have that kind of pathology. Okay, infimum. And this is called a minimal value. Alpha is called a minimal value. Minimal value. So, so I will not be repeating again that. So keep that the minimum value may exist all the time. Okay, but then if x exists, x is coming from here, as in star, okay, then x is called a minimum point. You know all these points, but let me recall it. X is called a minimum point. Okay. So minimal value, minimum point, where it is achieved. A point where minimum value is achieved is called a minimum point. And by infimum definition, in general, there will be a sequence approaching to that one. If xn is a sequence, if yn is a sequence, such that f of yn converges to alpha, that can, using the infimum definition, you can always, because the definition tells you that there is a sequence which is going to that one. And such a sequence is called a, then yn is called a minimizing sequence. Okay. So that's a 3 terminology, first you have to understand. So you want to do that 3 examples. So the minimum point, minimum value, and the minimum thing. All right. And you know that this problem may not have a solution. I'm going to show some through graphical examples. You can construct if you want the specific examples. I'll give through the graphical thing. You can precisely give. The infimum cannot have a solution. It can have multiple solutions. It can have unique solution. So looking for typical examples and through which we want to know what property you are looking for f so that it will have a solution. So you want to get motivated through the examples. So I'm going to plot some typical graphs. Okay. So look at this graph. You can take y equal to x square if you want it. Simple case where x equal to r, f is from r to r. That's enough. So you want to understand f from x to r first. And then you see what motivates you to define the definitions for that. This has a unique solution, right? So what is the minimum value? Minimum value is 0, minimum point is also 0, and it's unique. You don't have anything. So one of the things immediately come to your mind probably, if you are familiar with the things, what is called, it's a convex function. Right? If it is not convex, The smoothness not the issue right there. So if you have a point something like that, so you may have two minimal solutions, right? So you have this one. So you lose convexity. So convexity, so if you are familiar with some convex analysis, is good enough. So typically it's a convex analysis you have to study. Okay. So it's a thing. So you have two minimal points in this case. These are minimal points, and this is your minimal value. So you lose convexity and you have that. So another picture, so you see if you don't have convexity, looking for the uniqueness of the things you are losing. Okay. And another example I want to know, exactly similar function, but at 0 I don't define that. At the point 0, I define another value, say 1. That means anything, f0 is positive. You see this no minimal value, no solution. You see that, right? Because fx you can take it as x square. When x is different from 0, f0 is some number which is strictly positive, no solution to this problem. When I say solution, there's no solution. I changed it just 1. And I want to end of it, want to characterize what property is missing in the process. Okay. You may say continuity is there, but continuity missing may be a strong assumption. If you are looking for continuity, when you look for the functional which associated with, you may not have such things in the minimization problem. Yes, probably it's a continuity assumption, but you also have to see physical applications. So it's not directly post this kind of problem. You have many, many physical applications, physical models in your mind which you may lose things. But you see, it's not just changing. So immediately it's done that it's not the continuity always creates trouble. So I have something, same example, but I define f0 is equal to say -1, if you want it. In this case, you have a unique solution for the problem, right? My 0, so what is your minimal point? There exists unique solution. So you want to distinguish something like this, these two. Something to the one point you have changed it. And these 2 points makes immediately the existence of solution differently. Okay, and there is a solution, what is that? f0 is equal to -1. If you take any number, any negative number, then -1 is the minimal value and the minimum point is x. So you have a solution. This example led to what is an important notion in the minimization problem, which is what we are going to see, what we call it a lower semi-continuity. That's the motion. I will give you the definition. You have more general, I will define the definition in the context of metric space. But you can also define in general topological space the concept of lower semi-continuity. Okay? I will come to that. But I want to tell you something more serious issue. Okay? You have a function, something like this. And this function, it goes to like this. Okay? Can you tell me now whether this has a solution or not? What is infimum of f of y? Y in R? Obvious, right? Tell me. 0, right? So that is okay, but does it have a solution or not? Of course, right? f0 is equal to 0. So it has a unique solution. But then, I want to see, so I want to look at its minimizing sequence. Because you may not have these functions in such an explicit form. Eventually, if you see these two things, these 3 properties, the method of solving, I will tell you, do it in 1 dimension. Okay, method of doing it is that you derive a minimizing sequence which is available to you through the infimum definition. And then try to derive a convergence subsequence. So that's the first step will come. And if there is an f is continuous, you can immediately pass to the limit and you can get it. So when you have, yeah. Which one? No, this has an infimum, it doesn't have a solution. When I say solution, there is an X satisfying that. This doesn't have. Infimum, yes. Infimum of f of y equal to 0. But then there is no solution where the infimum is achieved because it's tending. Okay, there is no solution. Yes, infimum always exists. That's what in the beginning I told you. Yeah?
You should mention that that plot you said the value of the ceiling.
Yeah, so that's written. Yeah. This is equal to f0. Yeah, so there is no solution when it is positive. Yeah, when I say solution, and it is achieved. Okay, so it's not up to the graph, it is coming to the graph. Same graph, remove that 0 value, put it here. The more serious thing here, so the method will be take the minimizing sequence and then look for a convergence subsequence, then you know when it exists. So that is where the technical issues will come. Pass to the limit, then passing to the limit comes more issue on F. And you need continuity with respect to topologies which you are working. And in the homogenization you have seen the topologies are weak topology, not even point-wise topology. So the functions which you are coming, so you will have. The more serious thing is that you look at the minimizing sequence. So I can choose a minimizing sequence yn, which going to 0, so that f of yn also goes to 0. That's fine. But the more thing is that I can also choose yn goes to infinity. For example, I can choose in this case 1 over n. I can choose f of yn equal to n. Then in that case, f of yn, that's equal to f of n, which also goes to 0. So you see, you have a minimizing sequence of you start with an arbitrary function and choose that a minimizing sequence, and that minimizing sequence may not have a convergent subsequence. So you want to get rid of this graph. So you want to get rid of this graph, and that's what the notion developed what is called a lower semi-continuity. Now you don't want to happen that. In other words, whenever f of yn has some subsequential limits, I should be able to derive a convergent subsequence. Okay, that's led to the notion what is called the Coercine. Okay, so let me define these two notions. Okay, so definition: f from x to r is said to be lower semi-continuous. This is a notion in almost all the books follow this notation. So it's a universal notation, for example. Okay, and this is with respect to some topology, whatever topology is here. Okay, so lower semi-continuity, just like a continuity, it's all geometrical definitions. Okay, geometry involves topology. So it will say it's not any algebraic definition. Lower semi-continuous function, if for any xn converges to x, we have f of x less than or equal to lower limit of f of xn. F of xn may converge, but f of xn may not converge, but then it will have a lower limit, and f of x should satisfy the lower limit of that. Okay. There are more, as I said, you can do this definition also, general topological space, which is given in terms of inf, sup, etc. So let's not get into that one, but this is the definition. But in one dimension, let me give you what this means. You can prove it as an exercise. Okay, so I will give you what this corresponds in one dimension. What is actually your continuity? So let's go with the continuity. Okay, so if you have a continuity, you have a point here, you have your output function, right? This is you have to treat that way. You have an output. So continuity actually tells you, I want to measure my output with certain prescribed error. Can I make, how much error can be allowed in my input so that I achieved only that. I am within that prescribed error of continuity. That's essentially your epsilon greater than 0. Epsilon puts you the error you want. You can allowable maximum thing in your output, and delta precisely tells you how much error you can make in the. So that means that if you choose fx minus f epsilon, there should be a neighborhood. This is fx minus epsilon. This is in the one-dimensional interpretation, plus epsilon. I can choose x minus delta to x plus delta. Now I choose any y here. Y should go inside. That is what it tells you, a continuity of the function. But now let's look back your left continuity and right continuity. What it does, left continuity tells you, I have given this neighborhood again, but then I want to happen this only on the left side of this. For all y here, the image should be here. Right continuity tells you that for all neighborhood y here on the right side, this should happen. And hence f is continuous if and only if f is left and right continuous. But keep this in mind, but what is this lower semi-continuous tells? Generally, the more than the domain, the importance of the function is it's in the range. Okay, you can have a same domain, you can have different functions. So the more thing, if you want to understand the function, you want to understand the neighborhood of the function. Okay, and left continuity tells you that, and the lower semi-continuity tells you that you are not demanding giving a neighborhood here so that everything is inside. You are giving a lower neighbor part of it. That means you are putting fx minus f epsilon. So the given epsilon greater than 0, there exists a delta greater than 0 such that f of x, y is greater than or equal to f of x minus epsilon, and that should happen for all y in x minus delta to x plus delta. So basically you are putting, that's why this is more useful in, eventually you will see that's why it is more useful in the minimization problem. You want to understand the lower part of it. Okay, so that's, you can prove this definition is equivalent to, so you are demanding f of y is something. All right. And there is an equivalent upper semi-continuity. Okay, upper semi-continuity, we don't use it here. That is minus f is lower semi-continuous. Or you can write it in terms of the other way inequality with the limit supremum. So it's okay. So let's go to the cohesive definition. Yeah, now you see this. This is not lower semi-continuous. Not lower semi. This is an immediate example. Because if I take a neighborhood of this one, say half, then I want to choose a neighborhood in such a way that for every y it should be above that. But for every neighborhood, if you take it, it will be somewhere here. Okay, so if I choose smaller and smaller neighborhoods here, all these functions are below. So you don't get a neighborhood. But this is lower semi-continuous. Because if I choose a neighborhood here, epsilon here, everything is anyway above that. Okay, so this is a lower semi-continuous function. This is not a lower semi-continuous function. Cohesive. F from X to R is cohesive if for any sequence yn, f upper limit of f of yn, this is precisely writing what we want it, is finite. It may not exist a limit, but then yn has a convergent subsequence. Okay, you are demanding the cohesivity. You will have, there are various notions of cohesivity you will see all the time in PDE. Ellipticity is also a cohesivity. You may see the definition, non-linearity growth, what he has mentioned in the morning is a kind of cohesivity which has derived lower estimates with no mu per thing. When you divide it, it goes to infinity. So you need some sort of growth. Basically, cohesivity is a concept of compactness in some sense. That's what the convergence, right? So in some sense, in various forms, you are able to derive convergent subsequence. Derivation of convergent subsequence is a notion of compactness. You have to keep that definition instead of compactness, taking a definition as every open cover has a finite subcover. These are all good for MSc when you do an exam. But after that, you say your mind should be a compactness is a notion to derive convergent subsequence, which is not available when you go to infinite dimensional situation in general. Okay, that's the thing you should come to mind. So, kind of imposing a compactness notion in the infinite dimensional setup. Finite dimensional setup, you don't have to do that one. All right. So, these are the two things. F is coercive, and that is what we are going to set up. So, with this definition, you have a general abstract theorem. Then we will go to another section. So, we will do important sections for each of them. Okay. So, assume F is coercive and lower semi-continuous. Assume F from X to R bar is coercive and lower semi-continuous. Then whatever we want. So, you see the motivations and things we looked at, just finite thing, and formulation is not easy, but then these notions will allow you to talk about the minimization problem. Then star has a solution, star has a solution or minimum point, equivalent to saying that solution. As I said, you can't get uniqueness unless you have additional assumptions like convexity, like this example. Okay, this is a continuous function, it's also coercive. So, these are all coercive functions. This is not coercive. It's okay, not coercive. So, we are having all the examples. So, picked up these examples precisely. Okay. That's a minimum point, 1. And there are, this is the easiest theorem in the abstract setup. So, I will try to, it's a one-line proof. There is no complication proof like Antonio's lectures. That's a paper. Okay. So complicated, you are already in so many complicated things. Okay. So, any complicated thing, I am not doing it here. Okay. All that proof I will skip. It's not that it is not there. We don't have time. Yeah. Any limit point of a minimizing sequence, call a limit point or a cluster point, whichever notions you are looking at. Because this minimizing sequence may not converge, so look for all the limit points of a minimizing sequence is a minimum point. Okay. And 3, it tells you that, of course, if F is identically 0, nothing to do it. Identically infinity, nothing to do. Everything is infinity. Minimum is infinity. Everything will go to infinity. Then every minimizing sequence has a limit point. That's right. Here say that you take any minimizing sequence, then it is the limit of any minimizing sequence is a minimum point. Yes, that every minimizing sequence has a limit point. So what does this everything together concludes? It's enough to prove basically 3, right? Because you know that for every minimum problem has a minimizing sequence. The third thing tells you that it has a limit point, and that tells you in the second thing that that limit point has to be a minimum point. That means this is solved, if you see this. Okay, that's all you have to do it. So let me give, because it's quite easy, let me give you the proof. So let X, Y, and be a minimizing sequence. Assume that this is finite. If it is infinity, nothing to prove it. Okay. Okay. So assume that this is, yeah, that's assume F not identical is 0. So let Yn be a minimizing sequence. Okay. So what does coercivity tell you? When you have a sequence, this is finite by this assumption, if not identically 0, and then you assume this. If upper limit is infinity, you don't have to do anything. That's what so if upper limit is infinity or the limit is infinity, you don't have anything to do. So it's enough to do it. The limit of f of yn is finite. It's the only case you have to worry. If this is finite, coercivity implies coercive implies yn along a subsequence convergence. So, though I write it again yn, I don't distinguish subsequences. That's a kind of general thing which we are doing it. Okay, it's actually along a subsequence. Okay. Then what does that tells you? Yn is a minimizing sequence. So f of yn, the limit of f of yn is equal to limit of f of yn is equal to what? Infimum, right? Limit of f of yn is equal to f of y. It's a minimizing sequence. That's the meaning of a minimizing sequence. Okay. That is, of course, less than or equal to f of x. Is this clear? That's the meaning of a minimizing sequence. As a sequence is a minimizing sequence if f of yn converges to alpha. Alpha means this infimum. Okay? Yeah, alpha is the infimum. So in a minimizing sequence converges to that minimal value. This is by the infimum. But now apply the lower semi-continuity at this point. Okay? This comes from the coercivity property. This comes from the minimum property, lower semi-continuity, that is lower limit of f of y. So you have that. Okay. So that means this equal to this, and your problem is solved. Okay. If you are listening for this first time, it may take some time to get into the mind, so don't worry about that. All right. So let's go to something, next step, what we want to do it, because we want to come to a stage what we are doing it, right? We don't want to work in this generality. So we want to work when functional f is given by an integral function. Yeah. Which one?
The definition of coercivity and lower semi-continuity. So the theorem we are using x is the real value. But we define coercivity and lower semi-continuity real value.
No, you can't define. You can define for anything. That's fine. You don't need it. Yeah, we are so used to write R all the time. Okay. So our main interest is f is given by an integral functional. Why we do that one? In applications, if you have a physical system, this physical system will have an associated energy functional. Okay, and that energy functional will be the functional here. And in a physical system, minimizing the energy is an important aspect. That's a kind of stability basically, right? So you generally minimize in, suppose you have an elasticity system and if you have an applied force, and then you can write down its strain energy functional. So you want to know the displacement, which displacement this has the minimum energy. So associated generally function, there will be an associated functional. That functionals are energy functionals, And quite often these energy functionals are given by in terms of an integral. So you want to know what more we can do it when it is given, and that is what you are doing it for the last 1 week. And so I want to reformulate your PDE problem. I want to say that your PDE problem is a consequence of something else. The more primitive problems are minimization problem. So even if you look for historically 200, 300 years, most of the time you will be minimizing things. And the minimum things gives you your PDE. Okay, so the PDE is a kind of consequence of a minimization problem. So we are actually trying to attack your fundamental problems right there before coming to PDE. That's the concept of here which we are trying to do it. Okay, so let's do an example which you are familiar with it. And I want to, and yes, and then when you do a minimization problem, and then you are trying to look for a solution of that minimization problem given by an integral in terms of the integral functional, that solution you will see is your weak formulation. So that shows your weak formulation quite often is more fundamental than your PDE. And to get your PDE, you have to put extra assumptions on your weak formulation. So, so far you are studying, you are starting with the PDE and then you are developing its weak formulation. But actually that's not true. It's actually the most of the time it is the other way around. Okay? You know, that doesn't matter. Minimum problem can have still solution even if this is not satisfied. Yeah, lower semi-continuity will be lost.
No, it will not be lost.
No, if you put it up, it will.
No. You are having the zero. I will remove the zero from the domain. So you have r minus 0 as the domain and have y equal to x square.
No, I don't, the coercivity may be lost.
Coercivity because...
Yeah? Yeah, there. Yeah.
No, but you don't need completeness. You just need a topology that what...
I don't know, completeness is required or not.
So anyway,
no, I know, there will be a problem. There will be a sequence yn going to 0 that will not have a convergent subsequence in the domain. You take F0, that sequence. If you remove it, and then you take a infimum is 0 still, and then what is the minimizing sequence? Which goes to 0, right? But then the limit is 0, which is not in the domain. Yeah, coercivity. Good. So that's why good students will help the teachers to understand it. It looks like my answer is okay. Yeah. Yeah. So let's start with an example. So typical example which you are working. So let me not get into that one. So consider this functional. So you have a U. If you are comfortable after 2 lectures of Antonio, you take this 1p, okay, or 1p naught if you want, or you take, if you are not comfortable with the p, you take p equal to 2 and work with this. So it's better to work with this. I can do more. This may come later. We'll write more. Good. So you have a function f of v on this space for v in h1 naught of omega. You define an energy functional. This is really the energy in an elasticity system, I am telling you. In other cases, it may not be an energy. So the energy notion is developed corresponding to other PDEs as well. And we call it energy functional. Sometimes if the system is modeling some other problem, it may not be the energy functional. But in many physical systems, it is the energy functional. Integral of a of x gradient v of x dot gradient v of x minus integral of f of v of x. This is omega, this is omega. Okay. So what's your problem here? You want to minimize it. So you want to find u in h1 naught of omega such that f of u is equal to infimum f of v for v in h1 naught of omega. How do you solve this problem? Do you see this problem? Maybe those who have studied already PDE, have you seen this problem already? Anywhere? last 2 weeks, they are actually doing that. Of course, it's hidden there. It's the same problem. I want to see now what is that hidden thing which you may not have seen it. Have you seen this way or not? Those who have studied a course on PDE, of distribution theories of spaces would have definitely seen this problem. Okay, if not, you see it now. So how do you do this problem? How do you carry out there is a solution? So I'm not going to do that. Let's go to the elementary thing which you have studied in your graduation. Not even graduation, undergraduation. Let's do the simple problem. Suppose you have a function f from a, b to r, continuous. How do you do this problem of minimization? I want to find an x such that f of x is equal to find x in AB. I want to see how difficult things to carry out sometime. What are the things you need? F of y is in AB. How do you do this problem? How do you attack this problem? This is a one-dimensional problem which they may not. This is the first theorem you study in your BSc first year, right? That every continuous function in a closed interval has a minimum and maximum. You have studied, but how do you do this problem? That's what I'm asking. How do you make that statement? You have done that, right? Every continuous, so if you make a statement like that, every continuous function in a closed bounded interval, everyone knows that it has a minimum. I am asking that question here. I'm saying that there is a, so how do you, so you know that this has a solution. How do you do that? Tell me whatever you know something. Whatever you know, how do you carry out that problem? How do you solve it, I am asking. Or what the method you know to solve it? Is 0 and then? True. So you need, I have not given all that assumption, right? Even I am saying that continuity is an issue for me. You are telling that to do that, you need differentiability, which I want to come later. So that's an additional assumption. So you are not solving this problem. What are you solving then that way? Do you see that you are doing a converse, not the forward problem? What are you trying to prove first? If x is a solution and if f is differentiable, then f prime of x. Isn't it that a kind of reverse problem, right? So you are assuming that f is a solution, f is a solution, then you are telling that f prime is go, then you look for that it is then if you say that if f prime is a, you are coming back to that one. So that requires the differentiability, second differentiability of f. And we are in an infinite dimensional abstract normed space or metric space. So if at all you want to work out that method, you need all that notions to be developed, right? This is what precisely your advanced calculus which you have to study. Okay? So let's try to do it. What is the method to do it? Through the minimizing sequence. Please recall that. The method is that by an infimum, choose a minimizing sequence yn, which converges to alpha. If you recall it, this is to be alpha. And then yn belongs to AB, which is a compact set, and yn has a convergent subsequence. And f is continuous, so f of yn converges to f of x. You see, that's a procedure, and that's a procedure we want to adopt here now. And so that's the first step. So f is a continuous function, this has a solution. But now let's come to your thing. If x is a solution, right, this is what you are telling. So this is the first part which you want to do it, which you have to do it in an abstract problem. That's what in certain conditions you have done this. You see, you have not even done the continuity. You need coercivity and lower semi-continuity. With continuity and lower semi-continuity, I'm doing for continuity we already have. This is the method we adopted in general. But what you need is that the conditions more relevant to minimization problem. That's what you have to understand, this condition. Fine. So let's go to your second part. Second part is telling is that you are deriving a necessary condition. Okay, with the differentiability, you can only prove a necessary condition. To do that, your sufficient condition, you have to check your second derivative. That's much more complicated. So we want to see as minimum as possible. Okay? So if f is differentiable, so this is a necessary condition. You have to understand that. Necessary condition. Okay? If it's also called an optimality condition. Though there is no optimal control, I'm not talking about that. It's an optimal condition. You are looking for these are all optimal solutions, right? You are minimizing or maximizing or optimal or extremal solution. You are looking for that one. So necessary condition, what it says that if f is C1 and x is a solution, interior solution, then that implies f prime of x equal to 0. Got that point? So the issue is that you want to develop if at all you want to attack this problem to get, and this is for mathematicians, and this is for the practical engineers. Okay, they don't care you have a theorem or not. So what? There is a solution. If you cannot give me a recipe, what can I do with that with your lemma? Okay, so this is more practical, which you are, right? You do this one, solve that problem, get all possible solution, and you may have many solutions, and then even if you don't give a second condition, engineers may have a way to verify one of them can be the solution. So they take, so you are giving a basket of solutions from the necessary condition, and one of them possibly could be your solution. And then your mathematical lemma, existence and thing, you have a solution, you can go back it. So proving that existence uniqueness is independent of that is important, because all these solutions only a necessary condition. All right. So how do I do this one? So I need to have the concept of derivative. That's the next concept coming. Concept of derivative. Okay. And this derivative is also for a function where f is from x to r. You assume that f is a norm, etc. if you want it, or an Hilbert space. That's more important. So if you have a Hilbert space or a non-linear space, and this concept of total derivative. Okay, total derivative. I'm not going to introduce, if you have not learned that one, this is also called a Frechet derivative. Frechet. I hope this is correct, right? Yeah, because it's a French word. So I should be, if there are no French people here, I wouldn't mind putting that here or there anywhere. But some of them are sitting, I have to be careful, right? So it's mentioned correctly, Frechet. You need that, right? Okay. Okay. So this is called, how many of you heard about this Frechet derivative? Studied? Some? You have not heard? So, Frechet, I think so. Frechet, you have pronounced. Yeah, it doesn't matter. You put it. It matters for them. Okay. So there is a concept of a derivative. Okay, so given a function, you define the derivative at a point. I'm not going to give you the definition. You have to know what is the linear algebra. It is given via the linear functionals. Okay, so the Frechet derivative is an element in the dual. Okay, so it's a mapping from x prime to r. No, mapping from x to r, which is continuous. So it is in the dual. Okay, so that means f prime of u will act on v to give a real number. Okay, so without knowing the definition, you compute it. That's your x. It should be, of course. That's sorry. The most important component is linear. It should be a linear continuous. That's what I said, dual. Okay, so I mentioned it is in the dual. So Frechet derivative is a dual map. That means you are nonlinear map, you are trying to approximate by linear maps. And you are looking for the best linear approximation. So it's called a linearization process. So just like I said earlier, the compactness is, you have to understand, is a kind of finite property implementing it in an infinite dimension. The moment derivative comes to your mind, you should think that there is a kind of linearization happening. You should always, whatever be the situation, very complicated. The moment derivative, there will be some sort of a linearization procedure. Okay, fine. So what I do, so if you have not seen the derivative, you can understand it. But if you have seen it, is more comfortable. If you have not seen it, I'll give you a method I want to compute my Fresher derivative for this function. So I'm trying to derive this one. Okay, the first part is through that. The second part I want to say that if f is Fresher differentiable, I want to compute assuming f prime, that is Fresher, now I denote this Fresher differentiable, at u, where u is a minimum solution, which also assume that's what you want it, f is in C1, and then x is a solution. So we are assuming that u is a solution to this problem, okay, and then and f is differentiable, I want to compute my f prime of u. So the exercise is compute f prime of u. This is equivalent to say that compute f prime of u, u is fixed, which is the solution, and this has to compute for all v. That's the meaning, right? H1 naught. Because you want to action, you have to give the action of f prime of u for every v in H1 naught. Okay, that's it. How do you compute that? I'm going to do that's exercise which you can carry out back in your hostel room or wherever it is. So what you do is that you compute this f of u plus tv, okay, u plus tv, it's just like you do it, that's what you do it. When you do not know something, don't worry about that. That's how you learn math sometimes. If you are confused, if you don't know anything, do things blindly, assuming that my step is correct. Okay, that's why if you don't know how to justify, you have an intuition, you have an experience, do it. That's why we are all do research, right? We keep on doing it. Then we realize that everything is wrong. Go back. Okay, the interesting thing is that many steps will be correct. Only some of them will be wrong. And then correct it. If you do some 2-3 iteration, you will end up with a 1 point or 2 point where you are not able to set. And that's all your research paper, right? Once you set it, you get a research paper. Every research is like that. You keep on doing it, 1 or 2 steps will settle it, you are not there. Do that way, blindly do this computation. So you do this computation, this is how you calculate in 1 dimension, right? Do this and do this, limit t tends to infinity. This you can compute because this is in the inner product form. Because it's in the inner product form, computing that, this is a matrix, if I not told you, I thought you know it. This is a matrix, Aij of x. This is a matrix you are dealing with. Okay. So if you do that computation, you can see this is what you want to prove it. Don't worry about all these notions, just do this computation with that matrix. Even if you have not understood anything, which you can do, and you can see that this will become your familiar objects. You see? That's a familiar object which you are working for the last 2 years. And then you appeal this. This is what your expectation. If f is C1, x is a solution, my f prime has to be vanished because you are minimizing it at that place. So this is a kind of variation. You have to understand that u is your minimum solution. You take any other function and you put it, you are trying to make changes. When you try to put changes, it will only increase the energy. So inductions will come eventually. You understand that one, right? So this is the minimum solution, minimum value you are getting. Any changes, v is in h1 of omega, and for any t, u plus tv will be in h1 naught of omega, and that changes u. The moment it changes u, it has to increase. Okay, so immediately you will see that this is greater than or equal to, all that you will get it. Okay, so u is a solution. So thus if u is a solution, which you are already assumed, this you can do the computation without assuming u is a solution. Okay, this computation is independent of u is a solution. You can get that. So you can compute your derivative, Fresher derivative at any point. The computing, because it's a linear functional, you have to find its action at all points. and you do that one, this you expect f prime of u should, that's what you do it, equivalent to this one. Okay? And that also you can actually prove it, but let's not do that here, because immediately positive, but if other things you can change it t and minus t like that and all that you can do. Okay? And but what is the meaning of linear functional is 0? Linear functional is 0 means its action at every point is 0. What does that mean? This implies integral of a of x grade u of x grade v equal to integral of fv. It should happen for all v, h1 naught. And this is precisely your weak formulation you are studying. So what you are getting is that you have a solution to your minimization problem, and then if your function associated with this C1 according to the Fresher derivative, then that solution necessarily must satisfy your weak formulation. Now I don't want to call it a weak formulation right now, right? It is a solution interpreted it. My solution has to satisfy this integral equation. Okay, so this satisfy, it's important. Now PDE yet came here, you see. This is a fundamental problem and you came, no longer there is any PDE. It's only an integral equation as it. And this, if you, so that is why you try to prove the existence and uniqueness of that theorem. When you have an existence theorem, you are getting exactly the all possible solutions here. And if you have a uniqueness, then you don't have to verify. If you have many solutions, you have to verify which is your solution. If you have uniqueness, you know that only one solution, and then you know by theoretically this is a solution, this has to be that solution. You don't have to verify for a second thing. If you have a solution, that you know that there is a solution, and you are getting one solution for your weak formulation, you can prove that indeed is the solution to your minimization problem. Okay. So where does the PDE comes now? Let's do that. And you need to make now another assumption. Okay. So where did you get your solution now? That's again an exercise from the PDE. If you are not done in the PDE, you do that exercise. Your obtained solution is u is in h1 naught of omega. Okay. So assume u is in, this is how you put the classical solution. Okay. Assume u is in C2. Twice differentiable. I writing slightly stronger one. Let it be there. Okay. You don't need the twice that. You need only C2 intersection C omega bar. Maybe C2 omega bar is needed. So you take that U also in C2. How do you prove this? This comes from the PDE regularity result. Embedding theorems in the PDE. Okay? It comes from there. Okay? Once U is in C2, I can do and use your divergence theorem. I can do an integration by parts here. So the exercise is that integration by parts, which is available in the modern distribution theory, divergence theorem, whatever you want, you use it. And use your measure theory, whatever you want it will produce you minus Laplacian u equal to f in omega and u equal to 0 on d omega. You see, so you have extra assumption. Yeah. Yeah, I forgot. This is the problem you are studying. Now you see how my aim of the talk goes, right? You are already seen in the last week where A is varying. A grade U is sometimes difficult also having students who knows also, right? Okay, so they all right. See, we give everything correctly, they won't work out, right? While working out, they will. Okay, so you have your PDE. So your homogenization problem, which will come soon, is varying here. When you vary here, you have your. So you see, so you are trying to study this limit problem, right? So corresponding to a limit problem, there is an energy function here, PDE problem. with you take it all that. With that PDE problem, now it will be a varying f epsilon. So you want to know how, and you obtain some limit problem through homogenization. And you want to know that that limit problem can also be put back in your minimization problem. In other words, if you have a family of problems, you are trying to find the limit of a family of problems of this minimization. So you want to study not just for one function, you have a family of minimization problems, and then you want to understand the limit of that family of minimization problem. Can I get back my f? Okay, and that's what the concept of gamma convergence, which we want to do it. All right, we'll come, it will take time, as I said. But the advantage of gamma convergence, let me put it that way, you can actually not just do this one, whatever the monotone operators, the quasi-linear equations, everything, you don't need this form of integral. You can have much more general, which I will just tell you. I'll put some conditions. So I hope Harsha won't ask me why that condition. That conditions are standard because I'm not working out. I'm not doing it here anything. But I'll put, these are all some of the standard conditions. Whatever he stated are all standard conditions to study monotone operators. Without that conditions, the monotone operator, just like you have ellipticity and all that, in LP, W1P, you need all that conditions. Since epsilon is there, quite often you need conditions independent of epsilon. Growth condition, you can't have a very rapid growth. So if you have a PDE in which nonlinearity is highly growing, you may have a difficulty. That's why even your fluid equations, right? You have a, okay. So you have a more general equation of the form. So f of u is equal to integral of omega. I can write all this in this form and much more. I will come after this step. So let's consider this functional. Of course, this does not include what I stated. I want to replace it here by du. Then that function, that is a very special case of it. Now it's a more non-linear situation. There's no linearity. And the conditions for f is, one, assume, these are the two conditions you need to do it. F is something like a Carat-Theodore. So that means it's little more, but we don't impose that much condition for this one. This is lower semi-continuous. In LP, okay, yes, I will tell you where f is different. This is lower semi-continuous. The second condition is, this is nothing new. Those who know this nonlinear problem, these are the minimum conditions you have to put it to get that one. F of x of s greater than or equal to minus a of x plus r into mod s power p, okay, where 1 less than p, and this is for some a1 in L1, okay, and for some r positive, okay. So these are the kind of two conditions which you require to study this problem. And f is a mapping from, you can prove all that. F is a mapping from LP to, you can put even up to alpha. Okay, LP of omega. Any other condition? That's all I think. No, so yes, where is f map? My f map is from omega, you can also have from Rm to alpha. Okay, so you have these two conditions. This is about the lower semi-continuity with respect to the second variable, and then there is a lower growth. Okay, there is a growth here. Okay, this is only from the lower side, lower semi-continuity, so you get lower. If you want to have continuity, you may need the other way. Okay, so if you want your function, so you may need the bounds from other direction also. Okay, the proposition is that, so I have an immediate proposition. With that assumptions, f is lower semi-continuous. So we are looking for in this strong topology, strong topology. Strong topology means norm topology of LP. Okay. So you have your continuity. This proof is, you can maybe this is a 1 or 2 line proof. If if UN converges to UP, to check this is easy. UN converges to UP, U in LP. Strong topology means this is a strong convergence, and you want to prove that f of u is less than or equal to lower limit of f of UN. That's a lower semi-continuity, right? So to prove that, f of u less than or equal to, yes? Yeah, of course, that is there. P greater than 1 should work. Maybe P equal to 1 also will work. I think so. Because, yeah, at this stage you don't need all this. He is using, I later realized, he is using in his nonlinearity some other terms. So that's why the P greater than or equal to 2 for him. Later checked, we saw that. That's another term in his problem. Okay. This is easy. A proof is good. If UN converges to U in LP, you take this inequality. When you have this inequality, you will have A of x plus f of x of s plus r mod s power s p. This is a positive quantity. Okay. And by the lower semi-continuity, instead of s, I will put un of x. Here also, I will put un of x. Okay. So I can apply my lower semi-continuity. Of course, norm is a lower, the modulus is a lower semi-continuity. You don't lose. This is a fixed quantity. There is no problem of these are lower semi-continuous functions. So you get it easily. So you can apply the lower semi-continuity to entire this one. One is minus, right? This is minus. This will be less than or equal to, you may see the why A is necessary. A of x plus lower limit of this entire quantity here. Okay, you get that one. And but the UN converges, now you do the, how do you apply? I want this to be for f of u. So you take the integral and apply Fatou's lemma. Right? This is a non-negative functions. So you can take the limit, lower limit. So that's now you can continue. So you can apply the Fatou's lemma. When you apply the Fatou's lemma, you can take the integrals here. When you take the integrals here, you get integral here. But A is an L1 function, so that are all finite quantities. So you can remove this one after taking. So apply Fatou. Okay, to get the results. Because if you take integrals, this will go away because of A1, and then UN converges to U. So the limit is U power P, and then the, oh sorry, I made a mistake. I am applying the lower semi-continuity. So it should be without n here. F of x un of x minus r un of x power b. Yeah, that's the correct one. Okay, so we are applying the lower semi-continuity to this one. Okay, and you take an integral. Okay, when you take integral, this will converge, and that's an LP function. U is an LP function, so this and this will get cancelled, and your integral will get that, and that's exactly what you want it. Okay, the remaining terms will get cancelled. Yeah. Yeah. We will come to that. Okay. Yes, of course, it's not an easy tool to apply all homogenization. What he said, but I don't know how much we are not even talked much of characters here. Right?
No, I'm saying to put it in perspective.
You will come. You are coming for that. Yes. So you have the strong lower, but let me. So I have a little more time here. So I wanted to actually finish one more section. We didn't come to that. So I don't know how much I will do, but it's okay. Whatever you learn it properly. Okay. So you are interested in finding two other integrals. So this is a simple case I have told you, but then instead of these assumptions, if I make continuity assumption and modulus assumption less than or equal to this one, then you will have an assumption from the left side and you will have an assumption from the right side, and then you can put both f and minus f are lower semi-continuous, or f and both lower semi-continuous function and upper semi-continuity, and you can prove the continuity in similar lines. So if you have an estimate on both directions, you will be able to get your continuity of the function. Okay, so that are all corollaries which you can do. But my interest is two other functions. So let me see why these results can be applied. One is a function of this one. So I will quickly explain to you what we are doing. This function, and then you have your g of u. Yeah, g of u is equal to g of x of u of x. So you can make the similar assumptions on f and g, and you can prove certain lower semi-continuity of this one. And the important problem is to study the minimization problem over v of f of v plus g of v. And there are, with these assumptions, you will be able to prove the lower semi-continuity of such minimization problem. So you will see this includes a lot of general thing with, for example, a of x, du of x, which you are studied, which you have seen already, that kind of quasi-linear operators. So this will be, and it also involves the P Laplacian. For example, if you take this one, f of u equal to with respect to grade u power p, this also includes the minimization problem corresponding to this type of functions. Okay, when p equal to 2, you have your normal minimization problem, and you can also include ax and all that. So this class of functions, incorporates a lot of problems which you are already seen in the thing, plus some more problems in the nonlinear analysis. Okay. So what is the next step I want to do it? Okay. So there is a minimization problem, there is a constraint minimization problem associated with that. So you can also solve minimization not V in W1P. You can also pose the problem in a slightly more general setting over a K. And in certain cases, you need the convexity of that one. So let me not get into all that subtle details because that's more delicate. Okay, so you need the convexity, certain things, and you need some closeness property. And one of the major issues you face when you do homogenization problems and other variational problems is the lack of strong lower semi-continuous, because when you work with the W1P or H1, you do not get lower semi-continuity in the strong topology. Okay, but then but what you want is you may get strong lower semi-continuity, but what you require is a weak lower semi-continuity. Careful at this stage, weak lower semi-continuity is not a weak notion. Do you understand that? Whenever I say introduce a notion, we have an immediate feeling that that is weaker than the strong. It is not. It depends on whether the assumption is weak or a conclusion is weak. If you have the same assumption and if you are concluding a stronger result, if you are with the assumption we are concluding a weaker result, then it is a weak, it's a good thing, right? It's a weaker notion. You understand? If your weaker notion means you are having same assumption, concluding a weak conclusion. But on the other hand, if you are concluding the same conclusion with a weaker assumption, then it is a strong notion. Do you get me or not? Okay, so let me write it. If you have not got it, let me write it here. This is a crucial thing which you may have to see here. So what is weak lower semi-continuity? Under weak topology, That means under Xn converges to X weakly, you want to conclude the same thing. You understood this? This is a strong concept. Do you get that's a strong concept? Earlier, the strong lower semi-continuity, Xn converges to X strongly, you are concluding this. But now, you are concluding the same thing with a weaker topology. So that is called weak lower semi-continuity. So please keep that in mind all the time. Weak lower semi-continuity is a strong notion. There are many such things which may confuse you in topology. So you have to very clearly see whether the assumption is weak or a conclusion is weak. Do you know another notion like this? A stronger concept, weak something is stronger, basically. Exactly like a weakly closed. Weakly closed is a stronger concept. What is the meaning of a closed set? If Xn converges to X in that topology, then X is in that set, right? What is weakly closed means if Xn converges to X in the weak convergence, then you want to see that X is in that one. Okay? So the weakly closed is again a stronger concept. In other words, weakly closed always implies strong closeness. So you have to please careful these few notions. And so if a set is weakly closed, it is strongly closed, but the converse is true if that set is a convex set. So under convexity, you will be able to derive this kind of things. And that is what you may require to do. And that forces you to put certain conditions like convexity of F. Okay? So you have to understand why you put conditions. Okay, when you have the convexity and you are studying minimization problems, and you may need weakly closed things here. So the weak topology comes into play when you start doing PDE. So that's what I said, the convex analysis is something very deep. So one more section, little bit, I try to do it in another 10 minutes. So what are we doing it in the homogenization? What is the homogenization we will do normally? Okay, so that's again. So let me put it in a general way. Again, there are two reasons. So far we are working with just one function. But as in applications like in homogenization, you will have a family of functions. So, and the spaces may also be a family. So, like in homogenization or in perturbation, it need not be a homogenization problem. Okay, it can be a perturbation problem. So, the perturbation problem, you do it sometimes purposefully you can do the perturbation, or the physical problem may be a perturbed problem. The thing is that where your problem you are not able to handle, that's what sometimes suppose you don't have ellipticity, what you do, you add little viscosity, right, like in our equation. When you don't have it, you put little bit of viscosity or little bit of ellipticity. And then your perturbed problem will be elliptic. And then you study that problem. Okay, you do that one, it's like a conservation laws. Conservation laws, etc., like a PDE, if you have this type of problems, what is that? UUX equal to 0. This is a first order hyperbolic type equation, but this is a difficult to study. But then you put some epsilon here. This is a second order thing, very nice PDE, and you have a unique solution, all that can be studied. So this solution may depend on epsilon. So you want to know that whether U epsilon will converge you. So that's a kind of, so perturbation problems can come, you put it perturbation, or the perturbation comes in the functional, or in the space, like in homogenization, it's not perturbation, your PDE itself is oscillating type. So in other words, what I'm trying to say that, quite often, you end up working problems of this form. Fh of y, maybe in xh, this also can be done. So you would like to study and H is when H tends to 0. So it's not only the minimization problem you have studied for a function, you have the results, that's what in the so far I have discussed, but then you want to study, can you associate something like that? So this we are not handling because this is maybe a slightly easy thing to change it, because if you have a family of spaces, it may be possible to find an ambient space, big space X, so that you put every XH in X. Okay, you will be able to do it and redefine your FH by giving infinity outside. That will not change your infimum. You see, so I can define, if you have something like a family, I can define FH of tilde of X is equal to FH of X if X is in XH and equal to plus infinity if X is not in XH. That is X minus XH. That way, now this problem will be same as this problem of X. So quite often the varying spaces can be put it in a bigger space. And defining infimum doesn't change because outside you are defining plus infinity. So infimum cannot come from outside. So if this problem has an infimum, it will be here. So such tricks can be played. Okay. So the issue is to study a family of problems, and that is what we are looking at it, a convergence, right? And in a typical case like homogenization, what you have it in a homogenization problem, you have this problem now. Integral of A of x over epsilon, gradient of E epsilon, V, gradient of V minus integral of F over omega. And this is what you are interested in studying, this one. So what is gamma convergence to? So before I finish, so gamma convergence, so let me tell you the stage for the next one of my lecture and probably Harsha's lecture. So what we are trying to do is, you are trying to study this minimization problem. Okay, U epsilon is equal to infimum of F epsilon of V, where V is in H1 or W1P or whatever it is. So the gamma convergence attempt to find some F, okay, which we call it F naught or whatever it is, some limit of F, so that the minimal point, minimizing sequences, everything is adapted to the limit problem. Okay, so in other words, if you have a U epsilon, you are basically wants to see that U epsilon converges to U, and you have this kind of similar the minimizing sequences or a minimal value, and you want to see the convergence of F epsilon of U epsilon to F of U in F naught of U, and you see how the minimizing sequences goes there. So the gamma convergence trying to find out an F naught, which you already seen it in the homogenization. Homogenization, what you have seen in corresponding to this one, corresponding to epsilon, you know that A of x over epsilon always converges to average of A, right? This is a notation, right? You know that, which is a matrix. X or epsilon converges to. So you have a point-wise convergence immediately. This converges to integral of M of A, gradient of E minus F of. Okay. So you have an associated functional. This is what you are. So you have some point-wise limit, F of E. And then corresponding to that F of E, I can associate a minimization problem. But last 10 days, what you have seen is that this is not the problem. For this problem, for that problem, this won't happen. You do get some convergence, indeed, but then the minimizing energy, so the whole thing what you are doing in the last 10 days is understanding the energy, though probably whether they mentioned or not, you are trying to understand the energy functional. What are the important components you are trying to understand? You are trying to understand the convergence of these products. Okay, so whole business is this one. Once you understand this convergence, If this converges to M of A into grade V, everything is done. You don't have that one. But then, where does it converge? It can converge. First question. Second question is that if it converges, does it have the same form? So there are two different questions. One is the convergence of that one, and this converges you can easily determine. Because this is in an L infinity functions, this is an L2 convergence, and hence these are all L2 bounded sequences. And hence it definitely will converge to something. But what the last 4 to 10 days of lectures, what you have seen through homogenization, this limit is nothing of the same form. This is a very crucial thing. Okay, so it's not about the convergence. So the just it converges to something is an abstract theorem, and then finding the limit in the prescribed format is a different problem. In other words, your problems are started in the gamma convergence. You have a problem which is given by a family of problems, and it's a minimization problem. Proving the existence of this gamma convergence is a standard, very trivial, means once you introduce all that, you will get it from the abstract theorem immediately. So you can immediately prove without much difficulty, this F epsilon will converge to some F naught. Okay, you do get F naught, with the gamma, it will converge to gamma converge. The gamma convergence which is to be introduced by in the next lecture, you can indeed prove that. That's not the difficult part of it. But your F epsilons are given by an energy of a functional of the form integral functional. So the whole difficulty of gamma convergence is the integral representation. In other words, can I find something? So if F epsilon is in general, suppose F epsilon is given by in this form, that's what the general setup here. Okay, instead of that functional, in general, you will have a family of a thing, and you are looking for a function which is converges gamma, that you can do it, and then you can say that minimum etc. will converge, everything you can do it. So you do get F of naught, which is the gamma limit, quickly, but the question is that does there exist a function so that this is equal to F naught of x dux? And this is what is called the integral representation, and that is not possible to give. That you have to have some hours of lecture. It is highly technical, delicate, is not difficult. All complicated, it's a kind of complicated proof. It's not very easy. Okay. So what I will do this thing, I will introduce a simpler notion than gamma convergence in the afternoon, what is called a relaxation. What happens to, I want to understand gamma convergence in the constant of a constant sequence. Constant sequence means constant sequence of functionals. Instead of Fn, I have Fn equal to F. What would be its gamma convergence? What is the proper, so I want to motivate you in the afternoon, what is the property you are looking in the limit? Okay, so the gamma limit may be picking up some property which is lost by the point-wise convergence. So or weak convergence. The weak convergence and point-wise convergence loses its property during the limit process. And if you have an important two property of lower semi-continuity and coercivity, if that is lost during that one, we don't want to lose that lower semi-continuous property. So we want to get back here. It is exactly like a uniform convergence. If you have a family of sequence of functions which converges uniformly, and if Fn are continuous, then F is continuous. But on the hand, for point-wise convergence, the limit function need not be continuous. The continuity property is lost in the thing. So similarly, it's possible that the lower semi-continuity property will be lost in the point-wise convergence, and we want to get back that lower. And we will do that for a single function. When a constant, a sequence of functions which is not changing with respect to that method is called the relaxation. So we will do that one. As I said, integral representation cannot be given in general, but I hope Harsha will do it for a homogenization problem. You are doing for n equal to 1 or general n? Yeah, so even n equal to 1 is hard. Okay, so I will tell you even for a single constant function, constant sequence, it's difficult. Maybe we'll do that in the relaxed session. So afternoon we'll do that. Okay, have good lunch. Okay, bye.